Hello, thank you for joining us for Module 2B, Day 4 for Pre-Calculus, and we're going to be looking at the binomial theorem today. So, the binomial theorem is nothing more than this approach that gives us a method to expand a binomial, so something that is two terms raised to a power where that power is a positive integer, all right? And it has to do with the pattern that arises if I say, hey, a plus b times a plus b, right, times a plus b, that if I multiply this out a whole bunch of times, there's going to be a pattern that arises, okay? And this general form of the binomial theorem is seen here, right? Where this little piece right here gets called our binomial coefficient, right? And where n is a positive integer, right? Now, how does this formula up here work? It's much easier to see it when it's written out. And we'd say, hey, for example, to expand 2x plus 3y, that quantity to the fourth power, right? And so this would say 2x minus 3y, excuse me. So to expand 2x minus 3y, would take that power of 4, all right, and say, hey, have 4 and choose 0. Then I would have 4 and choose 1. Then have 4 and choose 2. Have 4 and choose 3. Have 4 and choose 4. Right, and then I would take my first term to the fourth power, right, and then my next term is going to be to the third power, then that first term to the second power, that first term to the first power, so that I'm decreasing the power each time. I'm decreasing the power each time for the first term. And the second term starts at the 0 power, then it goes to the first power, then to the second power, then to the third power, then to the fourth power. So it has this pattern. Okay. Another notation for the binomial coefficient is this piece, NCR, which is also known as a combination, right? So NR, the binomial coefficient, is the same as NCR, and it gives us a way of computing, right, how I can select a given number of elements from a total group where the order of selection does not matter, okay? But in general, right, if I have n being 0, then my binomial coefficient is just 1. If n choose 1, binomial coefficients are 1 and 1. And then these values, 1, 2, 1, this pattern, right? Then 1, 3, 3, 1, 1, 4, 6, 4, 1. This pattern continues so that if I come down the diagonals, I start with the 1. And then what I do is I add the two terms preceding in the row above. So 1 plus 4 is 5, right? 3 and 3 is 6, 4 and 6 is 10. 3 and 1 is 4, 6 and 4 is 10, right? 4 and 1 is 5, and my last term 1, all right? So this idea, right, this pattern relates directly to what we'll have from our binomial coefficient. So we'd say, hey, this is 1, 4, 6, 4, 1, based on a row n equals 4, right? 1, 4, 6, 4, 1 from row 4 of this triangular pattern, 1, 4, 6, 4, 1. Now, this triangular pattern in Western culture, known as Pascal's triangle, also known as Khayyam's triangle in the Persian culture, Tartaglia's triangle. Also in Western culture, Tartaglia was an Italian mathematician that wrote about this pattern before Pascal, who was a French mathematician. Yang-Hui's triangle, the stairs of Mount Meru, a whole bunch of different ones, okay? But it is a convenient way to remember that pattern for binomial coefficients, and by arranging the coefficients, I obtain an array where you obtain an array where each row corresponds to the coefficients in the binomial expansion. Well, like we said, Pascal's triangle is what we'll call it. It'll be the most common in Western countries, and that's based on the work of a famous French polymath, Blaise Pascal. So, if I want to find the expansion of x plus 2 to the fifth power by expanding x plus 2 squared, x plus 2 squared times x plus 2 and grouping like terms, that's how you would have done it in past experiences. So you could say, hey, I know that x plus 2 quantity squared is x squared plus 4x plus 4. So that means I would have x squared plus 4x plus 4 times x squared plus 4x plus 4. And if I multiplied things out, that would give me x to the fourth, right? Plus, if I distributed this direction, x to the fourth plus 4x cubed plus 4x squared. Then I'd have plus 4x squared, or 4x cubed, excuse me, right? Then I would have, so from there to there, then I'd have 16x squared plus 16x. Then I would get, let's distribute on that constant of the 4. All right, we have plus 4x squared plus 16x plus 16. And so that would give me, if I do that piece and I group terms, that's going to be x to the fourth, there's 4x cubed, another 4x cubed plus 8x cubed, right? Then I have 4x squared, 16x squared, and another 4x squared. That's going to be plus 24x squared. Then I'm going to have 16x and 16x, that's plus 32x. And then I finally have plus 16. All right. Now, how is it that this binomial expansion works within the patterns of multiplying things out? Well, let's consider how I could get x squared. Well, I could get x squared by multiplying x squared times 4, or I could get it by multiplying 4x times 4x, or I could get it by multiplying 4 times x squared. So I have 3 different ways of getting to my x squared, and that would give me 4 times the x squared times 4, the 4 times x squared, and the 4x times 4x, which gets me to the 24x squared. So that idea of recognizing, hey, I have a pattern that lets me know I have 3 ways of getting to x squared terms, and then seeing that in fact I do have 3 terms with x squared is what provides my pattern, right? And so if I were to come and look at my original piece and I say, hey, how could I have, right, x to the fourth? The only way I can get in this initial piece x to the fourth is to take 2x times 2x times 2x times 2x, right? So there's only one way to get x to the fourth. But what about for getting x cubed? I could have 2x times 2x times 2x, right, multiplying it 3 times if I was to distribute. But which of the 4 terms, right, that if I had multiplied it out, which of the 4 terms would be the 2x? So I would have 4 options, and that's how I get to my pattern, right? So coming back to this problem, I need to find this expansion by multiplying out. We can already see it's super tedious. And I have the first expansion of x squared, x plus 2 squared times x plus 2 squared. And now I need to multiply again by x plus 2. And so distributing this x to the fourth, I get x to the fifth plus 2x to the fourth plus 8x to the fourth plus 16x cubed plus 24x cubed plus 48x squared, continuing, plus 32x squared plus 64x plus 16x, right? I'll distribute that 16, and then finally plus 32. So if I was to group that all together, if I was to group that all together, what would I have? I would have, let's put this now in a different color. All right, I would have x to the fifth plus 10x to the fourth plus 16 plus 24. That's going to be 40x cubed. 48 and 32. Well, let's see what 48 and 32 is if we're not so hot at arithmetic. 48 plus 32. Right, so then that's plus 80x squared. Right, then 64 and 16. 64 plus 16. That's also 80x and then plus 32. So this would be my expansion of just going to something to the fifth power, which hopefully you see is super tedious and annoying to do. But binomial theorem gives us a faster way to do it. So how do we use binomial theorem? All right, so there's a pattern for us. So I look at my terms and I say, okay, I've got 5 as my exponent, and I'm going to go 5, choose 0, 5, choose 1, 5, choose 2, 5, choose 3, 5, choose 4, 5, choose 5. Okay, now what are going to be these binomial coefficients for each of those, right? If I want to just write the number out, that would be a 1, 5, 10, 10, 5, 1. Where did those numbers come from? They came from that fifth row of that special triangle, Yanqui's triangle, Khayyam's triangle, Tartaglia's triangle, the old method, Tartaglia's triangle, but we'll call it Pascal's triangle. Okay, so that's the first part. The next part is I look at my first term. My first term is x. So I have x to the fifth power. Then I'm going to have x to the fourth power. Then I'm going to have x to the third power. Then I'm going to have x to the second power. Then I'm going to have x to the first power, and finally x to the 0th power, which is 0. Right? Then I'm going to have my second term, which in this case is a positive 2, right? Positive 2 to the 0 power, then to the first power, then to the second power, then to the third power, then to the fourth power, and finally I'll have that positive 2 to the fifth power. So what does that mean? Now I can go through and following my pattern, I have x to the fifth power, right, and 2 to the 0 power is times 1. Then I have x to the fourth power, and 2 to the first is 2. Then I have x cubed, 2 squared is 4. Right, then I have x squared, 2 cubed is 8. Then I have x, 2 to the fourth is 16. And finally I have times 32, right? And I have plus, 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 plus. So simplifying that out, 1 times x to the fifth times 1 is x to the fifth. 5 times 2 times x to the fourth is 10x to the fourth. 10 times 4 times x cubed is 40x cubed. 10 times 8, that's 80x squared. 5 times 16, that's 80x. And then finally 1 times 32 plus 32. So notice we get to the exact same solution using our binomial theorem, but it gets us there in a more efficient, a more clean, a more neatly written approach. Okay, so that's going to be it for this video, and we'll continue with the examples in our next video as we continue with the binomial theorem and binomial expansions. Come back to watch the next one. Thank you for your time.